Hello everyone. I'm Mans Hai, a PhD graduate from Tsinghua University's Yao class. In this video, we'll unveil the mysterious veil surrounding the concept of infinity and definitively answer a long debated question. Why does 0.9 repeating equal 1? You'll also discover a textbook-free proof demonstrating why the square root of 2 is irrational. Learn how the first mathematical crisis was ultimately resolved, and understand why the first and second mathematical crises are deeply interconnected. We'll even explore how solving this puzzle provides the key to why 0.9 repeating equals 1. Ready? Hit that like button, share, and subscribe. Let's dive in. Back in elementary school, we were taught that. How do we handle division that doesn't terminate? Take 1 divided by 9. For example, if you work through the long division, you'll find it perpetually yields 1, never concluding, stretching into infinity. To address this, elementary schools introduced a notation with a dot above the digit to represent such numbers. For instance, this symbol signifies an endless repetition of ones. This very notation has sparked a long-standing debate. Which is greater, 0.9 repeating infinitely or 1? On this matter, there are two prevailing perspectives. The first asserts that 0.9 repeating is equal to 1, arguing that 0.9 repeating can be expressed as 9 multiplied by 0.1 repeating. Now, as we've just discussed, 0.1 repeating is equal to 1/9. See, that means it equals 1. Doesn't that sound perfectly reasonable? But then, there are others who disagree, arguing that 0.9 repeating is still less than 1. Why? Well, think back to how we compare two decimals, digit by digit, from left to right. By the time you compare the whole number parts, the winner is clear. 1 is simply 1, while 0.999 remains 0. So the following number is obviously larger. Both arguments seem reasonable, yet they contradict each other. So who is actually correct? In truth, to resolve this question, you must trace back to the definitions. What does that mean? In the informal notation used in elementary school, where 0.9 repeating is introduced, within the rigor of mathematics, what precise number does it actually represent? We don't know for certain. Even more fundamentally, when we write the equals sign within such a rigorous definition, how should we precisely understand the notion of equality? Therefore, in the sections to follow, we will guide you step by step through the journey of mathematically formalizing the real number system. Along the way, you'll discover that the first and second mathematical crises are deeply intertwined. Let us first turn the clock back to ancient Greece, 1,000 years ago. At that time, there lived a renowned master of mathematics, Pythagoras by name. His most celebrated achievement was the proposition of the Pythagorean theorem, which we commonly know as the Geoyugu theorem. In a right-angled triangle, the sum of the squares of the two legs equals the square of the hypotenuse. Look at the figure on the left. The table he is leaning on bears his famous 3 for 5 triangle principle. The Pythagorean school, in essence, was a group of followers guided by Pythagoras himself, forming a distinct intellectual tradition. This school upheld two fundamental tenets. The first was the belief that all things are number. They were deeply convinced that everything in the universe, at its core, could be expressed numerically. This idea, incidentally, profoundly influenced early computational theory. Take, for example, the videos you watch or the games you play. They are, fundamentally, nothing more than numerical constructs shaping your perception. Now, the second concept they firmly believed in is called all numbers are commensurable. HMM. You might wonder, what does all numbers are commensurable mean? And what exactly is commensurable? Simply put, commensurable means they can be measured by a common standard. So, what does measured imply? To put it plainly, it means finding a shared unit that can express them as whole number multiples of that unit. For example, consider these two line segments of different lengths. The Pythagorean school held the conviction that there must always exist some small, fundamental unit of measurement, such that the first segment can be expressed as an integer multiple of it. Then your second line segment is also an integer multiple of this unit length. In this way, these two numbers, or rather, the line segments, can be expressed as integer multiples of the same unit, meaning they share a common measure. The next question, then, is how to find this small unit that can measure them both. The answer, in fact, is something we all learned in elementary school. It is the method of successive subtraction, also known as the Euclidean algorithm. Each time, you subtract the smaller number from the larger one. For example, here, since 10 is greater than 6, subtract 6 from it. Then, since 6 is greater than 4, subtract 4 from 6. This process repeats in cycles. Within a finite number of steps, the two numbers will inevitably become equal. This equal quantity, this segment, is then extracted and becomes a common unit of measurement for both. Now, if you take this unit and compare it back to the original quantities, you will find that each original quantity is an exact integer multiple of it. For example, the first quantity is 8 times this unit, while the second is 5 times. This approach has another advantage. The two resulting integers are guaranteed to be co-prime. It transforms any given quantity into a pair of integers. Well, that sounds pretty straightforward, doesn't it? But some might wonder why insist on using line segments. WOULD and T plain old integers do the trick? This actually traces back to Euclid himself. Even in his foundational masterwork treatise, Elements, numbers were represented this way through line segments. Take, for instance, the theorem you see here. If the ratio of a to b equals that of c to d, and c to d equals 1 to f, then a to b must also equal 1 to f. That's all there is to it. In the mathematical framework of ancient Greece, the concept of ratio, what you see here is ratio, held a position of profound significance. What we commonly refer to as rational numbers is, in fact, a somewhat misleading translation. Although rational shares the same spelling as the term associated with Enlightenment-era reason, its meaning here carries a subtle distinction. The rational and rational number derives etymologically from ratio, that is, a proportional relationship. Thus, a more accurate translation and conceptualization would be ratio numbers. So, here's a really amusing meme that plays on this double entendre. You can see the imaginary unit in having an argument. Right, says get real, meaning be realistic. It's poking fun at imaginary numbers, which aren't part of the real numbers. Then the imaginary unit I retorts, be rational too. Which ties back to the pun we just discussed, the dual meaning of ratio and rational. Now, with this understanding that the ancient Greeks preferred using geometry to explore algebraic problems as a foundation, let us now explore how Hippasus demonstrated that the square root of 2 is an irrational number. This proof, in fact, differs somewhat from the version many encounter in textbooks. To begin, we know that the square root of 2 rises from an isosceles right triangle, with sides A, B, and C. If the lengths of the legs AB are equal to 1, then the hypotenuse AC must be equal to the square root of 2. So, next, Hippasus would use the method of successive subtraction we just mentioned, attempting to eliminate the common ratio between AB and AC in a finite number of steps. But how exactly does one accomplish this? First, we can draw an angle bisect from angle A. Let D be the intersection point with BC. Then draw a perpendicular from D to AC, with E as the foot of the perpendicular. Elementary geometry tells us that triangles ABD and ED are congruent by the angle-angle side theorem. Thus, we have ABA and BD Delaware. This allows the first step of alternate subtraction to transfer AB to A. Subtracting this segment from AC leaves us with C. Next, we can relocate AB downward by leveraging the property of isosceles triangles. Note here that the lower right triangle CD forms another isosceles right triangle. Therefore, we know CE equals Delaware. Consequently, we can first transfer CE to the position of Delaware. Furthermore, note that the earlier congruence reveals that BD is equal to Delaware. Thus, Delaware can again be relocated to BD. Now, through alternating subtraction, after subtracting this segment from BC and CE, only CD remains. Let us now examine these two line segments closely. What do you observe about the two segments whose common ratio we seek? If we invert their positions, you will find that they once again form the legs and hypotenuse of an isosceles right triangle, identical in proportion, returning you to the very beginning. This realization struck Hippasus immediately. The process is endless. You cannot come to a halt within a finite number of steps. This implies that there exists no common unit between 1 and the square root of 2, where both can be expressed as integer multiples of that unit. In other words, the square root of 2 cannot be represented as a ratio of 2 integers. This was truly a remarkable achievement, considering that the entire numerical framework had not yet been established at the time. They were unfamiliar with concepts like infinite repetition or non-repeating infinitesimals. Yet, Hippasus managed to demonstrate, through geometric reasoning, that the square root of 2 is an irrational number. Now, let us take a moment to reflect on what this astonishing counterexample truly signifies. Oftentimes, by examining existing knowledge and immersing ourselves in the historical perspective of the figures involved, reflecting on the dilemmas and uncertainties they faced, and contemplating potential solutions, can be immensely rewarding. It allows you to delve deeply into the essence of a definition, a concept, or even an entire discipline. The most remarkable part is that history often provides a reference answer for your consideration. Through such exercises and inquiries, your critical thinking skills will flourish. After all, this very process of reflection is the finest practice for innovation. For those living in that era, unraveling the core of the problem, resolving the crisis and confusion, and pioneering groundbreaking theories. This is innovation. Now, let us take a closer look at the Pythagoreans, their beliefs and the challenges they faced. For instance, draw a number line. We know that all numbers lie on this line, such as 0, 1, -3, to 0.5, and so on. The Pythagorean conviction was this: since the unit length of 1 can always be divided into arbitrarily small segments, the finer the division, the greater the precision of representation. Just like marking a ruler with evenly spaced ticks, The number line could be adorned with these meticulously aligned gradations. Their belief was that any number, no matter how large or small, could eventually align perfectly with a mark on the scale, provided the divisions were fine enough. But Hippasus revealed that to defy this very principle, he was delightfully mischievous in his proof. No matter how finely, how densely you divided the scale, you would always find that to refuse to land precisely on any mark. You could come infinitely close, yet never quite reach it. Thus, even the rational numbers, those expressible as ratios, could not encompass the entirety of numerical reality. Every point on this number line is densely, ubiquitously occupied. In fact, within any tiny interval, you can find infinitely many rational numbers. Yet, even the tightest weave has its gaps. The number line has holes. These holes are the irrational numbers. They cannot be expressed as the ratio of two integers. As you inch closer and closer to the value of the square root of 2, each finely marked step you take is a rational number. Yet the final destination, the square root of 2 itself, is not. It is as if you, Jung-san, after great effort, you ran a 10-kilometer race. But the moment you crossed the finish line, you turned into Lisi, and the medal went to Lisi instead. This is what we call the incompleteness of rational numbers. By the way, in a later video, I'll explain that. If you randomly pick a number uniformly between 0 and 1, the probability of it being rational is 0, while the probability of it being irrational is 1. In other words, when you try to cover the number line with rational numbers, it's not a matter of whether there are gaps, it's that almost everything is a gap. It barely covers anything at all. The specific reason for this is related to measure theory. If you're interested, we'll dedicate a future video to explore this in detail. But here's the thing, it presents a rather paradoxical problem. Look, there seem to be so many rational numbers. Like stepping on an anthill and crushing countless ants without even trying. No matter how tiny the interval, you'll always land on infinitely many rational s. And yet, the number line is somehow littered with irrational s, like the square root of 2. Numbers that can be expressed as ratios of integers, whose decimal expansions never repeat. Utterly chaotic and patternless. How does that make any sense? So this example shows just how unreliable human intuition and judgment can be. Pythagoras initially believed that by dividing the scale finely and densely enough, one could always make any number align perfectly with a mark. Yet, Hippasus demonstrated with rigorous logic that this was not so. The square root of 2 defied this expectation. How, then, should we construct the most rigorous logical framework to ensure that every real number on the number line can be precisely defined and described with absolute accuracy? Pause for a moment and consider your answer. Mathematics offers a standard solution. Use a process, an infinite process, to define such a number. What does this mean? For example, if I asked you to write out the square root of 2, you might keep writing its digits endlessly, one after another. Here, only by infinitely writing out every decimal digit of this square root of 2, can you truly claim to have written out and defined the square root of 2. If you stop at any finite step, it ceases to be the square root of 2. It becomes a finite decimal. And a finite decimal is a rational number. So, here we must introduce how real numbers are ultimately defined in mathematical structure. It is called the nested interval theorem. For instance, let us use this theorem to define the square root of 2. First, we locate the square root of 2 within an interval. We know that the square root of 2 lies between 1 and 2. each time we refine this interval further, defining the square root of 2 within a narrower range, confining it to an ever smaller interval, for instance, between 1 and 1.5, progressively tightening the bounds. We find it nestled between 1.25 and 1.5. This process repeats indefinitely, inching closer each time, shrinking the interval containing the square root of 2 to an increasingly minute span. On and on, until the length of the interval approaches 0, yielding an infinite, descending sequence, layers upon layers of nested intervals, each infinitesimally smaller than the last. And these intervals, take note, these very intervals collectively define the number we call the square root of 2. Therefore, in subsequent discussions when we refer to a real number, I hope what comes to mind is not an isolated point on the real number line, static, unconditional, and possessing infinite precision. Rather, envision it as a process of nested intervals, progressively narrowing and converging, because that is the most fundamental definition of every real number within the mathematical system. As conveyed by the nested interval theorem, every sequence of nested, shrinking intervals, whose widths tend to 0, uniquely corresponds to a single real number. Now, we can finally return to answer the initial question. The infinite repeating decimal 0.999 is, in essence, precisely such a shrinking interval. Every time you write a 9, it shrinks to the rightmost tenth of the interval. Thus, when you endlessly write 9s, you are, in essence, traversing an infinitely contracting interval, a nested sequence of intervals. Let us ponder carefully which number on the real number line can remain forever within this interval. That is right, only one can. So, the nested interval theorem tells you that this unique real number, this infinite repetition of 0.9, is mathematically identical to 1. Now, let us revisit the two mathematical crises. The first crisis arose from a simple isosceles right triangle. Hippasus discovered that the process of alternately subtracting the lengths of two sides continued endlessly. For the first time, humanity realized that there existed numbers which could not be expressed as a ratio of integers. In other words, there exists a sequence of rational numbers that continuously approaches a certain value. Yet the ultimate limit of this infinite approximation steps beyond the realm of rational numbers, becoming an irrational number. The essence of the second mathematical crisis lies in Newton's handling of derivatives. At one moment, he claimed that the increment h was not 0, and thus could be cancelled out in the numerator and denominator. Yet in the very next step, when reaching the final conclusion, he declared h to be 0, simply eliminating it altogether. Is h equal to 0 or not? The definition seems to waver back and forth, highly unrigorous. Upon closer reflection, you might notice a similarity between these two dilemmas. It lies in the nature of a process itself. When it evolves toward an infinite, unbounded limit, its original properties may vanish, and the outcome becomes entirely different. In other words, certain mathematical concepts and knowledge can only achieve qualitative transformation and thus complete their definitions through an endless process of approximation. For instance, the most fundamental definition of irrational numbers relies on the infinite convergence of rational numbers. Similarly, the derivative function arises from the ratio yx in the process where h approaches 0, infinitely yet never equals 0, eventually settling into that stable, limiting value. Here, we arrive at a pivotal gateway concept in advanced mathematics, the limit. Now you may understand why the first chapter of advanced mathematics always begins with limits. It serves as a critical watershed and stepping stone. Before it lies the finite, discrete mathematics of our primary and secondary education, while beyond it unfolds the continuous, infinite realm of advanced mathematics. In the next video, I will start with a classic textbook proof that the square root of 2 is irrational, unveiling the profound mystery behind this seemingly elegant demonstration, the method of infinite descent. What exactly is it? And what surprising applications might it hold? Moreover, I will explain why nearly all numbers are, in fact, irrational. Why does a 1 centimeter line segment contain as many points as the entire Earth? What profound philosophical meaning lies behind this? If you enjoyed our video, don't forget to like, share, and subscribe. If you'd like to watch more of our content, be sure to subscribe to our channel. To see more videos like this, make sure to follow me. Knowledge knows no bounds, yet the quest is never effortless. See you in the next episode.